Hope you're doing well. Give me a sec, let me turn up the mic. Sorry. Hope y'all are doing well. It's kind of rainy here. It's been kind of, well, not fun outside. So I made myself a cup of tea with my, with the microwave in the lounge. Yeah, I would never have contraband or anything. And I got myself some notes. And I got myself the online version of my chemistry textbook. Because, honestly, actually, you know what I should probably do? I should probably go turn on the night mode on my computer. Or the night light, I guess. Yes, please. Oh well, that did. Wow, that did nothing. No, it didn't. It just made it really hard to see. Let me turn up the brightness. Actually, I think the brightness is set up. Oh my god. Both my roommates are computer science majors, and so like, actually it's fine, I guess we don't need it. But basically both my roommates are computer science majors, and so like, I, by default, cannot fathom how typing is relaxing. Just like a relaxing sound for ASMR, but, well, no, that's not necessarily true. But laptop typing, like, let me open it. Something I could type in. Like, I can never possibly fathom that as being relaxing. So I'm gonna keep that to a minimum here. I could see how like a mechanical keyboard would be relaxing, but unfortunately it'd be kind of impractical for me to have one. I know some people who, despite having laptops, still use an accessory like keyboard, like a mechanical keyboard, which, firstly, I don't know what type of money you got, you know, I don't know how you're paying for school, I don't know if you're paying for school, you know, but, and secondly, like, it's just impractical, it's just another thing you have to carry around, but whatever, to each their own. Anyways, today we're going to be going over chapter 13.5 in Gilbert's 3rd edition, like, chemistry and atoms-based perspective textbook, or it might be atoms-based approach, whatever. I could show the textbook again, but it's in the previous video I made. But, anyways, we're talking about reaction mechanisms, yeah, kinetics. So, we ended the previous section, well, I ended my last video, which was on the previous section, with my mic breaking, but now I got it working again, so that's good. But they, in 13.4, ended with an equation that enables us to calculate the rate constant of a reaction and the reaction proceeds in the same way as no matter what temperature is. In other words, equation 1330 holds if the reaction happens the same set of collisions and involves the same sequence of bonds breaking in reactants and bonds forming products in both T1 and T2. The molecular steps define its reaction mechanism. Yeah, let me hover over that. Oh my god, reaction mechanism! A set of steps that describes how a reaction occurs at the molecular level. The mechanisms must be consistent with the rate law for the reaction. So, let me see if I could find something around me that I could use to demonstrate kinetic molecular theory, which is kind of what this goes off of. And I do have something. Let me see if the camera sees it. Pens! So basically, let's say these two pens are some gas molecules floating around. The speed at which they flow around is kind of, well, let's say they're in a box. which they bounce against the edges of the box is pressure, right? And the speed at which they fly around would be temperature. So this would be if it was like really hot. This would be if it's like kind of cold, right? But if they bounce into each other, with enough energy, so like enough energy that it would totally mess up my ASMR video of like, then that might cause a reaction. Okay, let me write down what time was that. Okay, around 5:50. Cool, thank you. Thank you, Samsung, for cool. So that was a little loud. Sorry about that. I'll edit it out. And if I didn't, yell at me in the comments and I'll edit it out. But kinetic molecular theory and how it contributes to reaction mechanisms. Yeah. I think I have way too much energy for this video. I might have way too much energy for this video. Sorry. I drank way too much caffeine today. But that's because I'm a STEM major and we live off caffeine. All of us do. So there's a chem tour video, which I'm not going to go to because I think it does sound. Plus, it'd be probably more relaxing. Ooh, I should start my Pomodoro clock. I read somewhere that 52-minute Pomodoros and 17-minute breaks in between was like the optimal like Pomodoro session length for getting into flow. And if you don't know what a flow state is, then I will totally make a video. Actually, I have Goleman's Emotional Intelligence on my shelf. So maybe I can make a video where I go over some of the chapters where it talks about like things that are more applicable to productivity. Of course, I'm no self-proclaimed productivity guru or anything like that. I'm not some like executive entrepreneur dude on YouTube making like a fucking stupid like morning routine video or anything, but I'm just a STEM gal, you know. Anyways, in this section, we explore how kinetics data helps chemists understand how chemical reactions actually happen. To obtain such data, they could test for the presence of products formed in preliminary steps. Technology helps chemists to follow many chemical reactions through the transformation of reactants to products in the time that it takes for individual covalent bonds to break and new ones to form. These processes occur as rapidly as the bonds vibrate. Am I recording? No. I meant on my computer. Because there's this little thing in the corner. I'm not sure if you can see my mouse. If you can't, I'm sorry. Anyways, blah blah blah, who cares? Elementary steps. It's writing sound time. I already have that as a heading. But I am going to take more notes because I still need to take notes on this. And I'm lazy. Well, not really lazy. I'll call it efficient. So, I'm making an ASMR video out of it too. So, elementary steps. NO2. And this thing. So, this is second order to NO2, meaning that for every that the concentration of the products in this goes up by like a magnitude of like 4 times if the amount of NO2 is doubled. That's how reaction order means. And a first order reaction is if the concentration of the reactant doubles. And a zero order reactant is if it's a 1-to-1 ratio. I'll make another video on this. So, I doubt you guys are here to learn chemistry, but you're probably here to fall asleep. And that's okay. It's okay if you just want to fall asleep. There's nothing better to fall asleep to than general chemistry. Of course, it's organic chemistry scares people. So maybe next year I guess I could do a poll. And that'll happen. I love living in a dorm. It's so lovely. When the walls are super thin and you have to be quiet. Like, either because roommates are studying or you're trying to make an ASMR video, you're just chilling here whispering into your microphone and you just like, in the background. It's very nice. Let me get some tea. Like I said, caffeine addict. Addict. Doesn't matter what the inflection on the A is. Yes, it does. It does matter. If you're a grammar nerd. But if you are a grammar nerd, I don't blame you, of course. So, anyways, this reaction is second order NO2 because it reveals NO2 molecules out of the atoms. Out of the atoms, two colliding NO2 molecules rearrange themselves to form two NO2 molecules and one NO2 molecule. So, one answer to this question is contained in the two-step reaction pathway shown in figure 13.22, which is probably directly below here. It's not. Yes, it is. Whatever. In the first step, a collision between two NO2 molecules produces a molecule of NO and a molecule of NO2. Oh, NO3. Why did my light just die? It's tired of me yapping. But steps in the mechanism involve transient activated complexes. So, if you're familiar with biology, you know when a substrate goes into an enzyme, that's called the substrate enzyme complex. And that's basically what it's talking about with an activated complex, just out of the molecular level. Even though an enzyme and a substrate are at a molecular level too. Basically, allow me to draw it for a sec. If my pen will cooperate. And if you guys can read my terrible handwriting. Sorry. That might have been loud. I'm not sure if you heard that. I low-key banged my clipboard against my mug. Anyways, let me get closer to the camera so that you guys can see. Without. So. Let me hold that there. So if you guys could see that. If you could read my terrible handwriting. And if you could see like the picture that I drew in general. It's like two puzzle pieces fitting together, kinda, sorta, a little bit. Yeah. It's the same thing with an enzyme and a substrate. I remembered it by thinking of an enzyme and a substrate like, it's funny because everyone generalizes STEM to just being science. Or engineering. Like, it's not just STEM. It's STEM. And it's occurred to me that most of the, like, technology, like, majors are just either engineering majors or science majors. If you think about the wording of the majors, like computer science, computer engineering, or like mechatronics, that's just engineering. Anyways, the bonds in the activated compounds of the second step rearrange so that the two oxygen atoms become bonded, forming a molecule of O2, and we combine a molecule of NO. I should probably say the compound name, nitrogen oxide. The molecule, not nitrogen trioxide, is an intermediate in this mechanism. So let me just write down the reaction as it occurs. So, step 1. Dude, my pen is not vibing today. Wait, what is bro yapping about? Hold on. Let me look at the equation. So I'm not sure if you guys can read the screen. Let me make sure you guys can read the screen. Oh my. You really can't read the screen without me. You probably still can't read the screen, but that's chill, I guess. I'll write it down. Whatever before was objectively incorrect. So once more, if you guys can mention my handwriting, I'll try to show this. Wow. So basically, what I basically described is that the first step produces NO3 as an intermediate because I think all the something about, well, I guess I don't know yet, do I? But basically the reaction happens in 2 steps, with NO3 formed as an intermediate, and then that NO3 forming NO and O2. Yeah. So yeah. And that could be something to do balanced reactions. Kind of like how you would do a systems of equations. In a way. So how does the concept of activation energy occur or apply to a 2-step reaction such as this? Oh, that makes sense. I think they're gonna say that the reaction energy between the collision of 2 molecules of NO2 wasn't enough to completely break the bonds between 1 molecule of the NO. Wait. Now I'm thinking AP physics. Because that reminds me of an inelastic reaction. So the 2 elementary The two elementary steps produce an energy profile with two maxima. In elementary step 1, coefficients between pairs of NO2 molecules result in the formation of an activated complex associated with the first transition state in figure 13.23. As this activated complex transforms into NO and NO3, or NO2, NO3, NO3, the energy of the system drops to the bottom of the trial between the two maxima. In elementary step 2, NO2 forms the activated complex associated with the second transition state. As these complexes transform into final products, the energy of the system drops to its final level. Figure 13.23 shows the energy barrier for elementary step 1 is much greater than for elementary step 2. The difference is consistent with the relative rates of the two steps. Step 1 is lower than step 2. If the reaction were to proceed in the reverse direction, as NO and NO3, O2 react, forming NO3. The energy barrier on the right would be the smaller of the two, and the elementary step would be the more rapid one. Experimental evidence supports these expectations. So, let me draw a graph. Let me get my pen to work first. Come on, pen, you're embarrassing me. It's Delta G because it does work. Once more, if you could read my terrible handwriting. And this lovely little figure here, which I totally did not just like do usually made this stand. So if you could read that, that's basically what I meant with the peak, or what they mean with the peaks and the maxima and stuff. Yeah. I've been recording for quite some time. And I don't wanna, I guess I could make a longer video, but I don't think I really want to. I'll be honest. Well, that's not necessarily true. I would like to make another, like, a longer video, but I don't think y'all want to sit through like another 10 minutes of me rambling. Plus, I would probably mess up and touch the mic, like more than like the acceptable number of times, and editable amount of times. So, hope you all enjoyed the video. Hope you all found it relaxing. And I hope you all have a great rest of your night. Or day if you are a daytime ASMR enjoyer. I don't blame you. And thank you for watching.